So welcome back, everybody. So you're being recorded now. So I'm basically, so class 6 is essentially an overview where you basically, so you build the model and now you want to essentially use your better estimates for statistical inference. So you actually want to understand, what do these coefficients mean? Are they actually significant, quote unquote? So you remember that if you include a binary variable into a regression model, you essentially are conducting a comparable analysis to a t-test, and you have the difference between both groups, where one group is 0 and the other group is 1, reflected as this quote unquote slope. So it's the change from 0 to 1 that essentially will give you the difference in your dependent variable yi. So if you have now in the same fashion, you essentially get now, based on the residuals, and we talked about this the other day. So you have a normal distribution around the mean of 0 with a variance sigma square. And this allows you, with the sample size, as you know, using the central limit theorem, to also build a standard error. And this standard error is really the point estimate around your coefficient. And based from that, you get to a p-value quite easily. So, so this is the simplest of all examples. So basically, you have x equals 1, x equals 1, x equals 0, and you have a mu1 and a mu0. And these two means, these are essentially what you compare. So the nomenclature here, don't let yourself get distracted by the nomenclature. So this is really, so yi for your group I is essentially normally distributed around a mean of mu0 with a variance of sigma square, where I is defined as individual 1 to k. So let's say you have 20 people, you have your n is 20, you have 1 to 10 is going to be, k is going to be 10, so you have 1 to k, where k is 10, and then you have k plus 1, which is 11, to n, which is 20, right? So this is how the nomenclature here is designed. So you have yi and you have yj, where your group j is k plus 1 to n. So essentially now you're basically doing nothing else but comparing the y bar 1 minus the y bar 2. This gives you the difference. So you're basically estimating mu1 and mu0. And if you remember back from page 614, you have all population parameter are indicated with Greek letters. So you have a mu, you have a standard deviation sigma. So when you have a sample, you're looking at the y bar and the y bar 0. So the y bar, these are basically, this is the nomenclature for indicating statistics in samples. So this is the difference. So you have in population, you have population parameters, which are Greek letters. And in samples, you have statistics, which are here y bar, for example. Or it can be an m. So there are various different nomenclatures for sample. But it's generally accepted that when you have a mean from a population or a standard deviation from a population, you have a mu and sigma. So, and what you do with a sample, you always mean to estimate difference between populations, right? So remember from page 614, you draw these random samples and get a random distribution, normally distributed as an assumption for the t-test of random samples. So essentially to estimate your y bar 1 minus your y bar 2, you get a sample of random samples from the same two samples that are representing the population, that basically build up this unlimited, or this infinite number of differences between those samples. So you get differences, and these differences are normally distributed under the assumption of a t-test. So these differences are basically distributing with a normal distribution around this difference that you see between your two samples, which is meant to reflect the true difference you see in the population. But this estimate of this difference may not necessarily be absolutely identical, and it varies with each sample that you have drawn. And these differences, these estimate of the true difference from the population varies around that mean estimate with a standard error of the mean. And this is the standard error of the mean of these differences. And this gets you to the t. So when you divide your y bar 1 minus your y bar 0, divided by the standard error, you're standardizing now your differences. And by that, you get a t-score. And in the t-test, you use this t-score that you have evaluated under the assumption that it's a two-tailed test. You essentially can now use this t-score for hypothesis testing. So for creating a p-value, where the p-value indicates that this difference that you see between both samples is seen as a true systematic difference and not just due to random chance. So this p, the p-value, that is to determine a statistical significance needs to be smaller than 5%, is essentially a reflection of a so-called type 1 error, as you very well remember from page 614. So this type 1 error is basically the rejection of a null hypothesis where there's no difference between y bar 1 and y bar 0. And although you shouldn't have rejected it. So you're rejecting something that you shouldn't have rejected, that's your type 1 error. And the p-value is essentially that this probability that you're rejecting something that you shouldn't have rejected. So under the assumption that you have determined an alpha of 5%, everything that is smaller than 5% will lead to rejection of the null hypothesis, and you assume these to be different. So now what does this mean for a regression model? So essentially you have the form of a regression model. You have yi equals beta 0 plus beta 1 xi plus the error, the residual error. The residual error is now n distributed, normally distributed around the mean of 0 with a variance of sigma square with an I ranging from 1 to n. So this being said, if you have now an estimate, like here, for example, let me zoom in a bit. If you have here an estimate, like here for gender, for sex, and you basically have, I don't know how it's coded here, but essentially you have this estimate has around that estimate a standard error that is essentially determined by your sample size and the variability of those residuals, your variant that comes from your residuals. So the resulting t-value is essentially the division of the estimate divided, which is the difference, divided by the standard error. And this gets you to a p-value, because looking at the t-score table, you can read and you can interpret the p-value, the resulting p-value from that t-value. So okay. Yeah, just to make so here's basically the numerical example, right? So you have the estimate is minus 0.2021 divided by 0.1149 gets you to minus 0.21, which we know from the t-score table is essentially corresponding with 2 times 0.417, which is non-significantly different. So this is essentially what we did for sex as a binary variable. So it gets a little trickier when you have a categorical variable that has more than one group, because you're running into the same problem then that you had with t-tests. So hypothetically, you could do a comparison if you have 3 or more groups. You could hypothetically do just like, and that's what you have learned in BIOS620. You can do pairwise comparison. So you have 3 groups. You do group 1, group 2, group 1, group 3, group 2 to group 3. So you do 3 comparison. You compare these 3 groups. The problem is with each comparison, you have a leftover risk of a type 1 error. And this is not just 5%. If you do 3 comparisons, this actually exponentially increases and is substantially larger now as a type 1 error, that you will reject something just due to chance. And for that very reason, you need some overarching p-value to see whether this factor or this categorical covariate is actually significantly associated with your dependent variable. And for this very reason, you're using here an F statistic, using a likelihood ratio test. So you're including now factor of completed high school, a factor of completed college. You remember the example, we have SPB as a function of age, sex, and education. So if we are, as the reference category, we have defined here, did not complete high school and did not complete college. So if you attended high school, you have a smaller SPB by minus 0.6. If you attended college, you have a smaller value of minus 0.44. So if you want to compare this now, you're doing this with an Anova. So you build your first fit here, not including EDU. Whereas you want to know whether there's a significant association between SPB and education. You create a second model, which is fit, which includes EDU, and then you compare in an Anova fit 1 and fit 2. And this allows you to essentially see whether with your 2 degrees of freedom for EDU, you essentially have significant difference. And this p-value is essentially the p-value that applies to the categorical variable of education at a p-value of 0.02. So that's just a continuation from including something like a binary variable and testing it with a t-score. This is the continuation where basically you have more than one group, so more than 2 groups, and you're basically using now an F statistic to determine whether there's a significant association. So this is the education. If any questions on that, sorry?
Just, could you just go up just one slide? Mm-hmm. Okay, so, or sorry, one more. Okay, no, maybe one more. I just wanted to make sure that I was making, so fit 1 is going to be basically, so getting in that example, we're doing fit 1 minus fit 0 over the standard error of fit 1 minus fit 0.
Yes, yeah. No, this is the t-score. So this is literally, you have one group, y bar 1, so this is one mean, and that's the group of the second group. So you're calculating the difference between both groups, between the means of both groups, and under the assumption that this is equivalent to that mean the difference in means that would be drawn repeatedly from each sample, and you calculate basically, let's assume you have a sample and you take a subsample of that sample from one group and another subsample from another group, you build difference and you throw your sample back in the pool, but you only keep the difference. And you do that an infinite number of times, you get a difference between group 1 and group 0 that is reflecting the difference between your population mean, mu1, and your population mean mu0. and you're assuming that that estimate you have from your sample at hand that you're studying is essentially yeah, and it's coming back, right?
Sorry, it's yeah, I got it.
Exactly.
There you're looking at the other factor, yeah.
Okay. Exactly. And now the education example is just a continuation of the same exercise. You have now not two groups, like a group 1 and group 2. Now you have 3 means, right? So you have a mean for not attended high school, not completed high school and college. And you have the mean of that group that completed high school. And then you have the mean of those that completed college. You're basically doing the same thing. You build 2 models, one containing age and sex, which are our continuous predictors in here. And then a second one that includes, in addition to that, education. And this gets you an F statistic like in the Anova, where you test the resulting F score, where you compare between group variability divided by within group variability. And by doing this, you get a value that is an F score, which you're comparing then on F score table against the the degrees of freedom between groups and in the numerator, and the degrees of freedom for the within groups. So the degrees of freedom within the groups, the degrees of freedom within, that essentially is in the denominator. And you're comparing this, and you get a responding p-value against an F-score distribution, which essentially is unimodal, right-skewed, and has only a one-tailed hypothesis that it pursues. So as soon as you exceed this critical value from the F-score table, you reject a null hypothesis. Same principle happens here. So this is essentially an F-score that if you would look up an F-score with a degree of freedom of 2, you would basically get a p-value, a p-value exceeding that critical value.
Okay. Thank you.
You're welcome. Yeah, the rest of it is pretty much on the lecture to be seen as well. So we have the next part was really the residual analysis, where we essentially testing the assumptions which are being made for the basis of linear regression. Where basically you have a normal distribution of the residual errors. Then you have that the mean of these residual errors essentially is 0, which is not, which is arithmetically has to be true, right? But this is essentially what I pointed out in the interpretation of the linear model at one point, that when mean and median in your printout, and you see the printout here, oh no, it's actually cut off. So you see in the printout of a residual, in a printout of a linear regression, you see the distribution of the residuals. So you know that as soon as the median is not equal to 0, that there's some skewness in there. And then you have the minimal and the maximal residual values. So if these are skewed in one direction, you would see that too, right? And that's the reason why, let's do a quick model. Just so I can tell you, because this is where it kind of overlaps the lecture with the lab. And this is where I think this is neat to look at now. So we have here, we're doing this, right here. Complete cases. So we basically, yeah, I'm gonna go through the code in a second. I just wanna finish my train of thought here. So we have here a fit1, which is essentially a model that predicts blood pressure as a function of male and age, just like I've just shown in the lab, in the lecture. So here we have the residual. This is the distribution of the residuals. So one of the assumptions of a linear regression is that the error is at a mean residual of 0 and distributes with a variance of sigma square. So if the median is not exactly 0, there's some form of a skewness going on. If the first quartile and the second quartile are also numerically not identical, also there's some skewness, right? And if this is a little bit more on the negative end, this is skewed a little bit to the left. So, but you have nevertheless, you have min and max, your max is actually larger. So it actually, it has some skewness in both directions. However, the majority of outliers are more pulling the data to the left. So there's more of an underestimate from the model. And we will see that on the QQ plot. We actually can analyze this now. So same here, would here, for example, be now there was the model, and this is exactly that comparison that I was referring to. So now we're including here the same two variables. We have male and age, and we have here education that essentially is here included also with an overall F statistic. And this is essentially an overall F statistic. But if we would compare this now with an Anova, so here we have an F statistic that basically establishes the significance of the entire model and the accuracy of that estimate, which is then also reflected here with the R squared, the adjusted R squared, which we discussed about yesterday. And so here with the Anova, you get exactly that printout that we've seen. So you have here, this is male and age, and education as a factor. And here you get the degrees of freedom, which are consistent with your observations. You have 4,030 observations here with 3 coefficients, 3 estimates, which is the intercept, age, and gender or sex. And here with 2 additional factors, which is the factor for high school and the factor for college. So this essentially gets you exactly to that Anova F score. So yeah, so back to the on the assumptions. And these are the assumptions that you basically are testing them with the model diagnostic plots. So you have a variance of sigma square, which is constant over the entire range of your predicting variables, of your independent variables. So this is called homoscedasticity. So this constant variance you also need to test. And secondly, you need to make sure that the error of your group J and the error of your group K, which we know now is the Y1 and the Y0 from before, the Y bar 1 and the Y bar 0. These 2 groups need to be independent from each other. So, and you can test all of this. And we will test this now quickly through. So here you have the likelihood ratio test, which is synonymous with the Anova. It is essentially the same principle. You essentially get the same. It's tested against the chi-squared distribution, but it follows the same principle. You're again comparing the inclusion of your education into the model, and you see that there's a difference, which is basically caused by the inclusion of education.
Okay.
Yeah.
Yeah, and then
yeah,
just checking, you would decide to use the LM test versus the Anova test because of the chi-squared.
Well, this is the difference. I don't think there's substantially a difference, and I think they both basically will yield comparable results. So, but that's actually, I'm going to put this on my list, whether there are substantial differences or there are use cases where we would prefer one over the other. Not to my knowledge, to be honest, but it's an interesting question. Thank you for asking it. I saw them to somewhat comparably applicable and usable. Okay. I'll research. I'll get back to you on that. I will mention it in the next class. Okay, then we have additionally, you can here, and this is how you programmatically approach it. So again, you have fit one, you have summary fit one with coef, you get the respective coefficients out of your model, of the summary of your model. So in coef table, you're getting your you get your coefficients into a table, which looks now in the way you've seen up there, coef table. So that's your coef table. Now you can pull out specific numbers from your coef table. And so if you do coef table 2.2, this gets you the value. Sorry for the hammering. There's some construction going on. So coef 2, 2 gets you the second row in the second column. Second row, second column. This gets you up to the 0.55. Male coef is now 2, 1, which is 2, 1, which is here 3.3. So if you want to calculate now the t-value, you do exactly that. So this is this t-value that I mentioned before. And this is how it's being calculated. So now let's go back to the assumptions. So this one's. So if you do the assumptions, you essentially assume normal distribution, the mean of 0. You do constant variance, and that both groups are independent from each other. You are now testing this using the MT-cars package, by essentially fitting, again, miles per gallon as a function of weight. You get a model, you do a summary. And now you basically, you can get the residuals of your model. And if you get res, you remember how we logged on the respective residuals, right? So you have a fitted function that goes through the scalar. And the residuals are essentially the difference between the observed data point to the predicted data point. So when you're looking at res, this is basically, and we've talked about this on Monday, this is the difference between the predicted and the observed data point. And if you go on fitted, this gives you essentially those fitted data points. So that's the predicted. So you have now real data points, which is essentially empty cars. We said MPG, right? So this is your real data.
Mm-hmm.
This is your predicted data, and these are the residuals. That's the difference of observed minus predicted. So if you want to plot this now, you can do this with the plot function. And basically, you get an overview of all your residuals as a function of individual entries. No, this is actually as y hat. So this is the plot of the residuals as a function of your predicted values. So why do you want to see that? Because you want to see that you have homoscedasticity in your data, that this variance doesn't change over the magnitude of your observation. So this is a lowest function that basically is kind of a smoothing function, a spline function, that basically gives you a feel. It should be entirely flat. It's not really as flat. So there's some arguments to make and some concerns to be had. You can additionally look at this in a quantile plot, which is a Q-norm plot. So there you have basically your sample quantiles versus your theoretical quantiles, and the difference of that is basically found along the line of identity. So here you see this deviation, right? This is the deviation we're observing here on this plot here on the sides. So these are the two that we've seen outlined over. These are oh no, these are these two outliers. So you can reproduce which outliers am I seeing, and where are they, and why are they there. So you can essentially look at each individual point, and the further they deviate from your line of identity, the more deviation and the more leverage they will have from your data. So now you can also depict this as a histogram, the residuals. Now you can run this quickly down. You get here, these are your residuals, and this is this hypothetically perfect, normally distributed curve the residuals should look like, and you can compare your actual data to the perfect data. So here you get, for example, so the y fit is a d norm of x fit with a mean of residuals and the standard deviation of residuals. So this is essentially your perfect, X fit, Y fit. Oh yeah. Yeah, so you basically have your sequence from minimal residual to maximal residuals with a length of 40. And you basically, 40 being the length of the entire data set. So you basically, no, why 40? Okay, no, but doesn't matter. Oh no, because of the outliers. So it's from min to max, not the individualized. Okay, so this basically simulates a perfect data set, and then with lines, with this command, you are now building an X fit, which is a sequence of number, basically sequencing from minimal to maximal, creating 40 entries. So Y fit is now a normal distribution, which is essentially merging your X fit and building on your X fit with a mean. So it's the number. It's basically building an equally long data set with a mean that is consistent with the mean, the actual mean of the residuals and the standard deviation of the residuals. And then you basically, with this function, with the line function, you're just building this red line that displays the perfect normal distribution, so that you can compare it against what a normal distribution would have looked like and what your actual data looked like. Okay. So with linearity, yes, with linearity, you can also test the linearity of your data, where you fit the lowest function and you see whether this is flat or changes in its relationship. And yeah, so Professor Sang also makes the point that when you look at a large data set, you essentially have a lot of data, right? So it's very hard to make conclusions and draw conclusions based on such a data set. So he states here that it's easier to basically build groups, categorize them, and build. Oops. Okay. Load the package. And once you actually loaded the package, you're actually able to slice your entire data set into 14 equally sized groups. So you have the cut function. So cut basically cuts your data set into 14. So G is going to be the number of groups, and it's going to cut it in 14 equal groups. And then so this is creating then a new categorical variable displaying 14 groups and assigns individuals in a certain magnitude. So basically stratifies them in 14 different groups as per the magnitude of each. And with the SPB groups, you're building now mean entries for each individual entry. So if you run the tabular function here, you get for the variable blood pressure, you get for each of the groups you get a mean, but you remove all the NAs. And just let's look at it for a second. This is this data set. I'm not going to show you. So these are the age groups, right? So you see here those age groups, and you're basically getting with the SPP group. So these are the respective strata. And with SPP mean groups, you get now for each of these groups means. So you get here 14 means. And if you plot them, you essentially get this overview. So you get 14 groups and you get 14 means. So
wait, they were already grouped, correct? That's what you were.
This was this command, yes. So you do here with the cut2 function that comes from the hmist package. So you basically load this package and you utilize the cut2 function to essentially stratify the 14 groups. And then basically you're just looking at how does this relationship look like. So this is actually, besides these initially flat associations, you basically have an increasing trend. You can do the same with BMI. You can do the same exercise with BMI. So this is how you test relationships between variables and not having to look at this huge scatter.
Okay.
And so Tracy had a question, which I just wanted to quickly talk about, because when you have non-linearity in your data set, or you have variance in your data set, so this is the answer key that the Forza given you. So we have now, so this is now a different data set. So this is the help RCT data set again. We want to investigate the associations between alcohol drinking and homelessness with the confounders of age, gender, and race, age, sex, and race. So here she particularly pointed towards an association she was interested in when it comes to this is fit one. So this is alcohol as function of homelessness, age, gender, age, sex, and race from the very same RCD data set. And with the Q norm, you see here there's quite some deviation on it. So there is definitely a problem in terms of normality. And this is confirmed by plotting the residuals, where you basically see quite some deviation. So one way to deal with that is to actually log transform your data. And this is a little, it's tricky, because you're changing then everything, because from that point on, the interpretation, and we can talk about this another time, the interpretation at this point is not as easy anymore as that you're just adding up. So you're multiplying the slope with the actual value, and then you're adding it to get to your actual estimate. Now it's getting a little trickier, because once you have log transformed, you basically can only, if you multiply your estimate with log 1.01, you basically get an estimate. So that 1.01 basically gets you an estimate of a 1% change. So you're getting then an estimate of your outcome based on a 1% change of your independent variable. So interpretation becomes much, much more complicated, but sometimes it's unfortunately necessary to do that. And if you do that, you're basically building it by building a new variable where you log transform RCT I1 as the alcohol consumption variable. And and this is Tracy's question. Why do you add in this transformation a +1? So Professor Sang is here outlining already. Was it Marcel or was it Professor Sang? So there's a trick that you're doing by essentially adding 1. And why do you need that trick? And that was Tracy's question. So, and let's look at it. So we have RCT log logi1 test. Oh no, we actually yes. We do log RCT I1. So now we have a log transformed new variable. We take RCT I1, which is here alcoholic beverages per day, I believe. So these are the drinks per day. Ooh, 102. No, it's maybe not per day, maybe it's week. Okay, so but if you log transform it, so you have here entries that are ranging basically from a 0 to 102 or some other high number of alcohol consumption of alcoholic beverages. If you log transform this now by just creating this new variable, why is it not advisable to do that? Because it contains zeros. It contains zeros, which essentially lead here to an absurdum in mathematics, because the log of 0 is actually not existent. It's not defined because it's not a real number, according to mathematicians, because it goes towards negative infinity for mathematical reasons I'm not qualified to explain. So what statisticians are doing, they're basically saying, okay, so I take the hit of accepting that it will be inaccurate, and I add 1 to my outcome that parallel shift my estimate, and then I log transform it. So the log will be a little bit, it will be less accurate, but it's better than having to deal with a loss of sample size. So see, now we have basically changed it, and now there weren't any zeros, and for that very reason you get a 0 with the estimate. So if you added 1, the log of 1 is essentially, as you know, 0, whereas a log of 0 is minus infinity. So if you add 1 to all your numbers, you could hypothetically, you could also do I'm just adding 1 to only those 0 entries. But if you do that, you're changing the distance from each of those variables. So it's actually, for regression, the actual magnitude is actually less important than the distance between the respective data points. So for this very reason, you're adding here 1. I hope that makes sense. I hope Tracy will come back to me in case there's additional questions on that. Okay, and these are basically the fits here. We look here at race groups, and all of this follows basically the same layout as we did it before. We do a normality checks, and we essentially see here our plots, and we can also do again, we do a fitted versus residual plot. We get the same outline, and now we have, with the log transformed, we could essentially also take all the skewness out. All right, any questions to that? Sorry.
No, and I think going back over it again is really helpful.
Okay, great.
The in relationship actually to Tracy's question, is there, so you were saying though that you said it wasn't the magnitude that they were measuring so much as the
distance,
separation,
right?
the distance.
So the difference between the respective entries, right? So
but
yeah.
there isn't a need to then take what comes out of the log and then like somehow like treat for knowing that it's a bit like a bit inaccurate estimate.
It's not really, because essentially what you get an estimate, and this estimate is helping you to employ that then on actual data, right? So if we have, let's do two different models. Let's do a model where we do what did we want to do? Log, RCT, log. Was a model that made sense. Okay, so we saw here in this model of fit1, we've seen deviations. Okay, so this was the model. So here we have alcohol consumptions basically being the outcome. So your interpretation now becomes different, because you basically get now, you need to transform, you need to retransform your log estimate, right? If I built this model versus I built this model, what is it now? Where's the log transformed? Yeah, here's the log transformed story. So if you are using now the log transformed versus the, oh wait, so we see here, so we see from the numeric summary that this is already entirely different. So we see here different numerically values, different magnitudes, right? So they are different, inherently different, because now they're log transformed. And they will also behave differently in the actual model. So here we have fit log I2. So the outcomes and the estimates and the coefficients are entirely different. So if you're comparing fit1, let's do summary fit2 versus summary fit1 as a comparison. They're entirely different, did you see? So these are two different models. So the interpretation changes then, because you need to account for the fact that you have now a log transformed model, a log transformed outcome. So there are differences. If you, for example, if you log transform the predictor, you can still approach the same outcome and still take the predictor in, and you would multiply it with the log of. So let's say you have an estimate of 0.53, you would multiply it with the log of 1.01 to get an estimate for 1% of change. So you basically take the 1.01, that is 1%, right? Dividing it by 100, you get an increase by 1%. And that coefficient can then be used to estimate the change of 1% in that particular predictor. So the same applies here, but it's a little bit more complex. The formula is a little bit more complex because you need to take it to the power of that coefficient. But I'm not going to go too deep into that, but it becomes just more difficult to predict it. And that's the take-home message, right? So by basically replacing the zeros with a 1 and setting the actual logarithmic transformed, the log transformed value for 1 then to 0, you essentially, you do little to the coefficient per se, to the estimate. The estimate doesn't change because of that, because it's reflecting the change in relationship of one unit change. It's always a relative change and it's not an absolute number. So if the distance between those entries and you shifted it only, you increased it by 1, that's all you did. So your actual relationship doesn't change, right? I hope that makes sense. It's really the slope.
Yeah, that does,
relative
yeah.
change. Yeah. Okay.
Yeah.
Great.
Thank you.
Yeah, this was pretty much all that was around lab 6. Lastly, I just want to mention, and you have the code, and so you have the code here for the heteroscedasticity. If you have heteroscedastic data, and I'm just flagging this. So you have the code in the RMD file. You have the Huber-White robust method, the aka sandwich standard error. So basically what you're doing with this approach is, this is a modified approach that allows to deal and accommodate non-constant variance data. So non-constant variance data is basically where your residuals, and we have looked at the y-resid as a function of y hat, right? That was this plot. If this variance changes over time, you basically have the so-called heteroscedasticity. Heteroscedasticity means that the variance changes over the range of your data, of your independent variable. And if that happens, you need different methods. And Huber-White robust sandwich method is one approach to do that. And it basically gives you a robust standard error that basically gives you the possibility to estimate your beta hat more accurately, more precisely, essentially, because it affects standard error. It's not accuracy, it's actually precision. So the estimate per se is not changing, but the standard error estimate is changing, and therefore you would display it with standard error of beta hat asterisk. What is to be kept in mind is that the p-value for beta asterisk will always be smaller. That needs to be kept in mind, because it removes and it makes the standard error less affected by the changes in the variance. So it kind of it takes the trajectories of that association into account. Does that make sense? Any questions?
Yeah, and so with that change in the standard error, with the p-value being possibly a bit higher or a bit lower. So then if you got a p-value of 0.049, for example, from the beta asterisk, then you might be inclined to not trust it.
Well, not trusting is hard to say. So you basically, everything is affected by sample size. Everything is affected by various factors, right? So the changes are usually not as dramatic. I haven't used it much. It's not the most common technique. You use it when you really have very specific regression questions or regression examples that you're working on. But if you get an estimate, you just gotta keep it in mind that you need to compare it, right? And this is the comparison that is also presented here. You need to make sure that if you have discrepancies between one versus another, you need to keep in mind, then you need to do residual diagnostics, and you look at the plots, you visually inspect it, and take your determination then. Not trusting it, discarding it, I'm shying away from using these terms. Just being aware, diagnosing it, and looking at it maybe with different methods. If you know they are different, If you, for example, you see here that the standard error is like a little bit smaller, right? This is from least square regression. This is from our Huber-White robust method. So essentially, if you see, if you see differences here, and they differ significantly, you will question the result, but not discarding it, not trusting it, but just, okay, then you go the extra route. You use an additional method. You confirm your findings. You will present this in that fashion to in your paper that essentially will then be reviewed. First, this review, and you can make your point. Yes, I considered it, and this is what you found, and with the other method, and you confirm it. Right? Nothing is with certainty. You never can be 100% certain. It's like we're dealing with probabilities essentially. So there's always a probability you're rejecting something you shouldn't have rejected. It's just a matter of fact that this can happen. So for this very reason, it's like you try to confirm as good as you can. Does that answer your question? All right. Any other questions?
Yeah, it does. Thank you.
Thank you. All right. So then
Not right.
no more. Okay. Well then, good luck with the assignment. Good luck with the homework. I'll be back on Monday. I'll post the timings. And Monday next week, if anything in between, use the discussion board, email me, let's get on one-on-one if needed, and let's move on with our journey. Class 7 comes out on Friday. Next week, the midterm will be posted on Sunday night.
Okay.
All right.
Thank you.
Good. Thank you.
All right.
Nice week.
Bye.
See you soon. Bye-bye.